Today we're talking about Chapter 10, a t-test for two independent samples. Most research studies compare two or more sets of data. When the data from two completely different independent participants group is called an independent measures or a between subjects design. That's what we'll be talking about today. Think of this as two separate classrooms with different people in each classroom. Data from the same or related participant groups is called a within subjects or repeated measures design, and we'll be talking about that in our next chapter. Here is an example of what we'll be looking at. Here's population A, taught by method A. Think of this as one classroom. We don't know the population mean. Here's population B, taught by method B, totally separate classroom. And again, we don't know the population mean. So we're going to take a sample from each population. The null hypothesis says the difference between these samples is equal to 0, or there's no difference. Or if you rearrange the equation, the mean of the first sample equals the mean of the second sample, meaning there's no difference. The alternate hypothesis for the independent measures t-test says that there is a difference. Mean 1 minus mean 2 is not equal to 0, or the mean from sample 1 is not equal to the mean from the population of sample 2. The next slides reference the middle column of the t-test equation sheet. Get the equation sheet out now and follow along. The basic structure of the t-statistic for an independent measures t-test looks like this. T is equal to the difference of means of the samples minus the difference of means from the population over the estimated standard error. Before we can solve these, we need to find a pooled variance. Basically, we're looking at the variance from the first population and the variance of the second population, and we're pooling it together into one variance in order to help us find standard error. So the pooled variance is equal to sum of squares for the first sample plus the sum of squares for the second sample divided by the degrees of freedom for the first sample plus the degrees of freedom for the second sample. Let's look at the estimated standard error for the difference between the two means. The equation for this is the square root of the pooled variance over n for the first sample plus the pooled variance over n for the second sample. Let's talk about degrees of freedom. A pooled estimate allows for the larger sample to carry more weight. This means if I had 10 people in sample 1 and 30 people in sample 2, the estimate for sample 2 would carry much more weight because there's more people. So the degrees of freedom we can either calculate as degrees of freedom for each separate sample, df1 plus df2, which would give us n1 minus 1 plus n2 minus 1. Or you could combine those together and say that the df pooled is equal to n1 plus n2 minus 2. Either way is fine. Here's an example. Given n1 is equal to 10 and n2 equals 10, find the pooled degrees of freedom. Pause this video while you do the calculation. So here's either way of doing it, but either way is fine. Degrees of freedom would equal 10 minus 1 for the first sample, plus 10 minus 1 for the second sample, which would give us 9 plus 9, which equals 18. Or you could use the other definition of degrees of freedom pooled, which would be n plus n minus 2, which is 10 plus 10 minus 2, which again gives us 18. Either way is fine. An independent measures hypothesis test uses the same 4 steps as the other hypothesis test we've discussed. State the hypothesis and select an alpha level. Locate the critical region. Again, draw your picture. Collect the data and calculate the t-statistic. Make a decision. Here's an example. This is example 10.2 from the text, so feel free to look up the textbook. you're given that the degrees of freedom is equal to 14 when pooled together. Alpha level is 0.05. Take a minute and look up in your tables, the t-statistic table, to see if you could find where the critical regions are. You should have found t is equal to plus and minus 2.145. Here's the assumptions for an independent measures test. Independent observations, which are observations with each sample must be completely independent. For example, one classroom has completely different people than another classroom. Normal population, this means each population that the samples came from must be normal. And homogeneity of variance, this is a new one. It says that the two populations must have equal variances. Let's look at variance. The larger the variance, the larger the error, meaning that they're more spread apart, so the error is bigger. The larger variance also produces a smaller value for the t-statistic. However, a larger sample produces a larger value for the t-statistic. Let's look at Hartley's Fmax test. This is a test for homogeneity of variance. I know that's a long word. It just applies to the t-test. So when looking for homogeneity of variance, here's your equation. The large value indicates a large difference between sample variance. A small value indicates a small sample variance. Use a directional test or a one-tailed test when predicting a specific direction. Locate the critical region in the appropriate tail, and then report the use of one tail in the research report at the end of your sentence. Measuring effect size. If the null hypothesis is rejected, the effect size should be determined by using either Cohen's d, which is given by mean 1 minus mean 2 over the square root of the pooled variance, or percent of variance explained, given by the equation r squared equals t squared over t squared plus degrees of freedom. Confidence intervals. The difference of M1 minus M2 is used to measure the estimate for the population mean difference. Here's the equation for confidence intervals. Again, this equation is at the bottom of your equation sheet. The confidence interval is equal to mean 1 minus mean 2 of the sample plus or minus t times the estimated standard error. And remember, the t here is found by making a new graph with two tails and looking up the value in the table. Estimation can provide an indication of the size of the treatment effect. Estimation of confidence intervals can provide an indication of the significance of the effect. If the interval contains a 0, then it is not a significant effect. If the interval does not contain 0, the treatment effect was significant. So here's an example. You can look at this example. It's example 10.6 in your textbook. Here's a confidence interval. So here's a 95% confidence interval for mean 1 minus mean 2 of the population. It goes from 0.782 up to 7.218. Notice that it does not cover 0. This is where the null hypothesis would be, where the mean 1 equals mean 2. So in this case, mean 1 does not equal 1, 2. 0 is not included, so it is significant. In the literature, report whether the difference between the two groups was significant or not. Report descriptive statistics, mean and standard deviation for each group. Report the t-statistic and the degrees of freedom, and report a p-value. Report the confidence interval immediately after t. Example, 90% CI goes from 6.156 to 9.785. Let's talk about variance and sample size. Because a larger variance leads to a larger error, it also leads to a smaller t. Because larger samples produce smaller error, larger samples lead to a larger t. Again, here's one final example of two different samples. Treatment 1 is taken from a population that has a sample of 9 people. The mean is 8, and S is equal to 1.22. For treatment 2, which has 9 people, the mean is 13 and S equals 1.22. Go to your equation sheet, see if you can solve this problem. You can pause this video while you do so. You should have found that T of 16 is equal to 8.62, the probability is less than 0.01, and both measures of effect size indicate a large treatment effect. D is equal to 4.10 and R squared equals 0.82.